Elementary Statistics, practice test number 4, module 4, chapters 8 and 9. Chapter 8, hypothesis testing. Chapter 9, inferences from two samples. We're looking at chapter 8, hypothesis testing. A test of hypothesis is always about a population parameter. The observed value of a test statistic is the value that we calculate for a sample statistic. As the sample size gets larger, both type 1 and type 2 errors decrease. Type 1 error is defined as rejecting a null hypothesis when it's true, false positive also called. Type 2 error, failing to reject a null hypothesis when it's false, also known as false negative. The value of alpha is called the probability of type 1 error. It's equal to that value. The value of beta is the probability of type 2 error. It's equal to that value. And 1 minus beta is called the power of the test, would be the correct decision, probability of rejecting a false hypothesis.
In 1990, 5.8% of job applicants who were tested for drugs failed the test. At the 0.01 significance level, test the claim that the failure rate is now lower if a simple random sample of 1,520 current job applicants results in 58 failures. Does the result suggest that fewer job applicants now use drugs?
The parts that you see, I'm going to go over the concept, what's happening with those parts, A, B, C, D. So let us write the given, the very first number, 5.8%. That is the proportion. The next number, 0.01, that is the choice of alpha. As we move on, the sample size, N is 1520, and X is 58. Now, P is 0.058, Q is 1 minus P, and it ends up being 0.942. The product of NP and NQ, if they are large, that means we can use normal distribution. Now, how large? In some texts, they go with 5. In some texts, they go with 10. And the two are way larger than 10 in this case. Also, we need to calculate the p hat, which is x over n. This is the test statistic for proportion. Z is p hat minus p over the square root of pq over n. So we are ready to move on. Before we do that, here's the test of hypothesis. Generally speaking, it has 4 steps. The first step, you write down the H0, the null hypothesis, and H1 or HA, the alternative hypothesis. You also write where the claim goes and whether we have a left tail test, right tail test, or two tail test. The next step, we calculate the test statistic. The third step, we either calculate the critical value or we go with the p-value. I'm going to discuss both concepts. And finally, you make a decision. All of them result in part A and part A only. You reject or fail to reject H0. Then you go back to the first step and you write parts B and C regarding the claim being true and restate the decision. That's really the idea behind the first few. And of course, we can do the p-value and the rest of it. Let's get that started. So in this case, we have the given P is 0.058, Q was calculated at 0.942, alpha 0.01, P hat 0.03816. So we are ready to move on. First and foremost, H0, P is 0.058, H1, P is less than 0.058. Less than makes it left tail test, and this happened to be the claim. Let's calculate the test statistic using this formula. Basically put that into the formula, resulting in the following, negative 3.309. So that's the test statistic. Critical value comes from the choice of alpha, and Z is between the two numbers. It is important to know that we are approximating proportion by normal distribution, and we only use Z. We never ever go to T distribution. Now, if we do the drawing, we notice that this is the location of a critical value, roughly negative 2.33. And the test statistic is way into the tail or the rejection region. Therefore, we reject H0. So I want you to stick with the very first step. We are going to reject H0. What about the rest? You have to go back to the first step and make a decision. So if you are rejecting H0, that means you're okay with H1, you're accepting H1, and the claim becomes true. So stick with that. And now reinstate. There is sufficient evidence to support the claim that the failure rate among job applicants for drugs is now lower. Result suggests that fewer job applicants now use drugs. Either way is fine. As far as the p-value is concerned, let's discuss the concept. When we look at the p-value, it depends whether it's a one-tailed test or a two-tailed test. If it is a left-tailed test, the area to the left of test statistic. If it's a right-tailed test, the area to the right of test statistic. If it's a two-tailed test, the test statistic calculator is either negative, that means area to the left of it times 2, or it is positive, that means the area to the right of it times 2. In this case, the Z is negative 3.309. The p-value is the area to the left of that. In other words, write this. If you look at this drawing, the area to the left of negative 3.31. That's as far as the graph is concerned. Now, the p-value, looking up the table, technology, you name it, we end up with 0.0005, and it's way less than the choice of alpha of 0.01, and we make the same decision, namely reject the null hypothesis. When the p-value is less than alpha, reject the null hypothesis. The next part is asking, what is type 1 error? What is the probability of making type 1 error? If you recall, type 1 error was defined as rejecting H0 when H0 is true. So for this question, rejecting the claim that the failure rate of job applicants who were tested for drugs is 5.8%, when the percentage is actually 5.8%. So if we reject that when it's actually 5.8%, it's considered type 1 error. And it is always equal to the choice of alpha, which happened to be 0.01 for this question. If we were to do it with technology, we use the proportion Z test. We put the information in. That means we put the P, X, N, and we choose less than. We do the calculation, and it results in the following. Now notice the test statistic, this value, is almost identical to what we have. Needless to say, they use more decimals. Look at the next one. This is the p-value, and this p-value, it is 4.6727354. E minus 4 means times 10 to the power of negative 4. The meaning of this is multiply this number by 10 to the power of negative 4, which means this decimal must move to the left because it's negative by 4. This is a scientific notation.
A sample of 54 bears has a mean weight of 182.9 pounds. Let's assume that the standard deviation of weights of all such bears is known to be 121.8 pounds at alpha equals 0.1. Is there enough evidence to support the claim that the population mean of all such bear weights is less than 200 pounds?
Let's write the given one by one. Sample of 54, that's N. The mean weight of 182.9 pounds. This goes back to those 54 bears, therefore it's X bar. Now let's assume that the standard deviation for all, that means this number is sigma, all. Pay attention, somehow all is implied. Either explicitly or implicitly. So sigma is 121.8, alpha is 0.1, and we are testing this claim, therefore mu is 200 pounds. Be very careful as you write those. By the way, most of the time, alpha is chosen as 0.05 out there. I want you to know that. So let's start. The first step, H0, mu is 200. H1 mu is less than 200. This is a left-hand test, and that is the claim. Let's calculate the test statistic. Z is X bar minus mu over sigma over square root of n. Again, everything is given here, just plug in. And it results in the following, negative 1.0317. Critical value alpha is 0.1. Since sigma is given, is known, we go with the Z distribution. Z becomes negative 1.285, looking up the table. Let's do the drawing. The critical value of negative 1.285 and the test statistic is way into the non-rejection region, negative 1.0317. So fail to reject the null hypothesis. Now, if we are not rejecting the null hypothesis, what happens? We go back to step one to make that decision. We are not rejecting H0. What are we rejecting? H1. So we are rejecting the claim. In essence, the claim becomes false. There is not sufficient evidence to support the claim that the population mean of all bear weights is less than 200 pounds. If we were to do this by technology, TI calculator mean Z test, and we plug in the information mu, sigma, X bar, N, and this is less than, we do the calculation, it results in the following. Notice, this is our test statistic, needless to say, with a lot more decimals. This is the p-value, 0.15. That is larger than alpha of 0.1. We make the same decision, which means fail to reject the null hypothesis.
16 new textbooks in the college bookstore had prices with a mean of $70.41 and a standard deviation of $19.70. Use a 0.05 significance level to test the claim that the mean price of a textbook at this college is less than $75. Assume normal population.
So what is given? So take a look. The numbers that you see here, 16, that is N. Now this is the mean. Does this go back to the 16 or to all? This goes back to 16. Those 16 had a mean of, so therefore it's X bar. Now what about this standard deviation? Does it go back to those 16 or to all? It goes back to those 16, therefore it's S. Alpha is 0.05, mu is 75. So pay attention to the given. In real world, we are almost always dealing with a case like this such that sigma is missing. So having said that, H0 mu is 75, H1 mu is less than 75, which makes it a left-tail test. And that's a claim simply because it says less than. That's what we are checking. Test statistic can be calculated using this formula. It's very similar to Z. This time it's divided by S over square root of n. You do the math and you end up with negative 0.9320. Now alpha is 0.05. Degrees of freedom is n minus 1, which makes it 15. And if we go with the table, on the left column, we go down until we hit degrees of freedom of 15. And when we come across area in one tail is 0.05 because it's a left tail test. So the answer is 1.753. Because it's left tail test, we make it negative if we were to use the table. So the table gives us positive, we make it negative. And to make a decision, we look at the graph and we see that the critical value of negative 1.753 is here. The test statistic is here, way into the non-rejection region, failed to reject H0 or the null hypothesis. So going back to the first step, if we are not rejecting H0, we are rejecting H1, we are rejecting the claim becomes false, and we keep on writing. There is not sufficient evidence to support the claim that the mean price of a textbook at this college is less than $75. Again, for the technology, we would use mean t-test. We plug in the values as follows: mu, x bar, s, n, whatever this one is, less than, greater than, or not equal. You do the calculation, and it will give you the following. Notice this is your test statistic. This is the one we calculated. This is the p-value, let's say 0.18, which is larger than alpha 0.05, and we have the same decision, which is failed to reject the null hypothesis.
Tests in the author's past statistics classes have scores with a standard deviation equal to 14.1. One of his current classes now has 27 test scores with a standard deviation of 9.3. Use a 0.01 significance level to test the claim that this current class has less variation than past classes. Does a lower standard deviation suggest that the current class is doing better? Assume the population is normal.
What is given? Standard deviation for the past statistic classes, that means sigma. N is 27. Now those 27 have a standard deviation of 9.3, that means S. So you want to distinguish between S and sigma, which one is which. Alpha is given as 0.01. Let's get started. This is extremely important. H0 sigma is 14.1, H1 sigma is less than 14.1, which makes it a claim and a left tail test. So let's use this test statistic, plug in the information, and calculate. So we are plugging in everything that we have here. That's why the given is important. We end up with 11.311. As far as the critical value is concerned, choice of alpha, degrees of freedom of n minus 1. This is a chi-squared distribution. We need the area to the right. So chi-squared needs two things. Degrees of freedom on the left column, you find it. And the area to the right is 1 minus alpha of 0.01, resulting in 0.99. So area to the right of the critical value. This is the limitation of a table, and it results in the following. So the chi-squared has a value of 12.198 for the critical value. The drawing, we notice that the critical value is way into the rejection area, so we are going to reject the null hypothesis. Compare the two. Test statistic is 11.311, which is less than the critical value. And remember, the chi-squared starts from 0 and goes to infinity. It doesn't have a negative value. With that being the case, reject the null hypothesis, the claim becomes true. So to answer part B, you have to go back to the first step. If you're rejecting H0, you are accepting H1, loosely put, and the claim becomes true. There is sufficient evidence to support the claim that this current class has less variation than past classes. A lower standard deviation doesn't suggest that the current class is doing better. It just means that the grade is more homogeneous, closer to the mean. Mean value might be different. If we were to do this by technology, we could calculate the chi-squared value given the CDF, which results in the p-value. P-value is, for this question, 0.005, let's say 6, which is less than alpha of 0.01. We get to the same decision, rejecting the null hypothesis. So here's the technology. We are rounding it over here.
Consider a population of frogs living on an island. We believe that the frogs may be members of a species called Rana pipiens. The mean length of Rana pipiens is told to be 11 centimeters. The following length values in centimeters were obtained for a sample of individuals from the island. Do these frogs have sizes that are consistent with them being run at PPNs or not? Are these frogs run at PPNs or not? Use a 0.05 significance level.
What's happening, the assumption is, according to biologists, if we can come up with 11, if the test of hypothesis results in 11, that means they are, otherwise they are not. So we run a test. And the very first thing we need to do is to come up with some information here. So what do we need to come up with? What is the size? What is n? What is x bar? So you have to calculate the x bar. Again, this can be done by technology. You don't have to do it by hand, but you know what the formula is. Summation of x over n. You have to come up with the standard deviation S. A summation of x minus x bar quantity squared over n minus 1, take a root. Alpha is 0.05, mu is 11 centimeters. So this is coming from the data. Having said that, the first thing is H0 mu is 11. That would be the claim. H1 mu is not 11, and it makes it a two-tailed test. What it means is that if we are going to go with H0, then it becomes the type of frogs we are looking for. Otherwise, it's not. That's the way the test goes. So with that being the case, let's calculate the test statistic using the formula. So this is statistics at work, and it results in the following test statistic. Critical value, choice of alpha is 0.05. Degrees of freedom of n minus 1, 20 minus 1 results in 19. And the critical value becomes plus minus 2.093 from the table. So as we look at the graph, we notice that the test statistic of negative 2.3491 it's in the left tail. Therefore, it's way into the rejection region, and we are going to reject the null hypothesis. So stick with the first part, rejecting the null hypothesis. What does it mean? You go to the first step, you're rejecting the null hypothesis. That means mu is not 11. That means the claim is false. So there is not sufficient evidence to support the claim that these frogs have sizes that are consistent with them being Rana pipiens. Therefore, these are not Rana pipiens. As far as technology, this would be the technology that you could run it with Excel, and that's what I did here. You can run it with TI. It is absolutely up to you. Makes no difference.